Okay. Well, let's continue on with Coulomb's law. And now things are going to get a little more complicated, because our next unit is Coulomb's law for advanced coordinate systems. Okay, so let's just, we're going to now introduce the spherical and the cylindrical coordinate system and solve some field problems that way, because it allows us to analyze some much cooler types of systems. So I will give you an example of the type of system that we will do our first example from. How many people have a DLP projector at their house, or have maybe worked in it in their office? Know what that is? I don't think that's one of them. But the smaller ones have that dynamic light projection chip in it from Texas Instrument. Anybody have one of those or seen one of those work? No? We have 50 Okay. You do? Okay, good. I thought statistically we have 50 students that are living in a cave if nobody has ever seen this before. But, this is something that came out maybe 10 years ago from Texas Instrument. They had the patent on it, the original device that they fabricated. It's an example of a MEMS device, micro electromechanical system. And it's actually pretty cool. So let's say you want to project an image. You take a really strong light and you shine it. And you got to have some optics there as well. But you reflect it off a mirror and then shine it through some optics, which then projects it outward onto some sort of screen. And you get an image. I don't know if anybody has a type of screen projection system in their home, but these are common enough where people are starting to put them in their homes because the cost is dropping down. These chips are relatively inexpensive now, because they've been out for a while. But how they work is really interesting. So if this was just a mirror, this would be like the most boring device on earth, right? You can't project anything with a mirror. But if you blow this thing up, what they actually have is a bunch of mirrors, tiny little mirrors, 1,000 something by 800 something or whatever resolution you're using. And these mirrors are on pivots. So if you apply a voltage, you can deflect them. When you reset them, they come back and will reflect the light through the lens. If they deflect, then they're just deflecting light off in a direction that you can't see it, towards, say, like an absorptive area inside the projector. And these things can operate very quickly. The nice thing about going down to the microscopic scale is a lot of the friction and the wear type things that go on at our macroscopic level don't necessarily apply to the same degree. So literally, you can oscillate these mirrors billions and billions of times over their lifetime. Doesn't do anything to them. They still function fine. And so if you can do this quickly enough, you can actually generate an image, a moving image, right? So you got your reflection here, and you take your mirror, and if you want a black pixel, you deflect it. If you want a white pixel, you let it up. What if you want a gray pixel? Well, you oscillate it a couple times, depending on the intensity. That's how fast you can do these. What if you want a color pixel? Well, it turns out that there's a little color wheel here that has red, green, and blue, and it repeats itself a couple times, and it just spins around. So if you synchronize your mirror flipping with red, green, and blue, and you're updating the image fast enough, you get your eye blurs the combination of red, green, and blue together. It actually makes for a very nice image. If you get really close on the screen, you can see what's often called the screen door effect, and that is you can kind of make out the gray edges of the pixels, the mirrors that are being deflected to generate this image. Not a bad way. In fact, that people have actually talked about, I don't know if this is widely available, but putting these kind of chips in like your smartphone so that you could project an image onto like the wall or something like that and watch whatever, a movie. So what does this look like at the microscopic level, and how can we analyze the electric fields of it? So let me draw up the scenario that we're going to be talking about. And this is going to be an approximation. The actual device is a little more complicated than this, but this will give us a good handle on how to analyze more complicated problems. So we got our chip surface. And this is, of course, a dynamic light projection chip, DLP. Now, we're going to have a pivot. And there's going to be a conductive table on here. And this will have a charge density on it. We're going to call this plus rho sub 1. And this is a conductive bottom here. And this will have a minus rho sub 2. Now let me draw this a little bit angled, because this is the actual problem that we're going to solve. If you apply a positive voltage to this table here, what's going to happen, you're going to get positive charges build up on here. Negative charges will be depleted from the chip surface. This will be your ground plane. And so it should have roughly a uniform distribution of negative charges. And we could almost view it as a semi-infinite plane, because these devices are so tiny, and there are lots of them nearby as well. But we're just going to look in Model 1 device. So if you put a positive charge on there by applying a voltage, the table is going to tip down a little bit. It's actually going to deflect to an angle, we'll call it phi naught. And I think in my problem, I'm going to make this a square table. They're usually square. Let me draw this a little better. L dimensions this way, L dimensions this way. And then a height of D at the pivot. So you see how that works? You get positive charges on the table, and positive charges are attracted to the negative charges on the ground plane there, and that will apply a force, a relatively uniform force, that tilts the table a little bit and causes the mirror to deflect. Now the mirror actually rides on top of this assembly. It's not a conductor. It's a little dielectric and silvered piece. So you put that on top. We're just going to look at the charge table underneath of it. So, okay, how do we set this up? Well, we could use the Cartesian coordinate system, because we've got this plane here, this infinite plane. That's just like the problem that we solved. In fact, here's a rule. If we have already solved part of your problem in this class, go ahead and use the solution. You don't have to solve it again. So something simple like a line charge, an infinite line charge, or a line charge with minus A to plus A, or an infinite sheet charge. We already know what the answer to that is. So here's what we're going to do. I want to find the field at an arbitrary point in space, E as a function of R. And I'm going to basically have two contributions. I'm going to have E sub 1, which is the contribution due to the charge on this pivoting table. And then I've got E sub 2, which is the charge due to this bottom part, the minus rho sub 2. Fortunately, we've already solved that problem. We solved it 10 minutes ago in a previous lecture segment. This is going to be minus rho sub s over 2 epsilon naught, because this is free space above here, and we're going to be pointing in the z direction if z is actually the direction that we point up there. I'm actually going to change that around to solve E sub 1 because it makes it easier to change the coordinate system around and kind of bend the problem so that it's convenient for us. Okay. Now here's the problem. This table has a tilt in it. So I could actually do this E sub 1 calculation in the Cartesian coordinate system, but that gives me these things like limits with variables of integration in them because I've got a tilted plane that becomes a function of x, y, and z together. It's doable, but it's not fun. There's a much more elegant way to work out this problem, and that's the way we're going to choose to do it here. And that is using the cylindrical coordinate system. What I'm going to do, because I'm going to lay it down so that the z-axis is in this direction. The x-axis will be over here in this direction, x. And the y-axis will be, let's see, I gotta make this right-handed. Yep, did it. Whew. Oh, force of habit. Y, there we go. And so the origin's going to be here. I'm going to align the origin so that it's kind of at the edge of this system. The x-axis lines up with the edge of the pivot, and the xy plane lines up with the edge of this. If you get clever about how you choose your coordinate system, you can greatly simplify a lot of these problems that we study. So now, let's go ahead and set this up. But first, I got to review a little bit of the spherical coordinate system because we haven't used that yet in this class. It's important to review this in electromagnetics because electrical engineers do things different than mathematics and physicists, mathematicians and physicists. When you were in your calculus class, what did you learn were your variables for expressing, say, a position in cylindrical coordinates? Yeah, what variable did you use for that distance? R, yeah. Unlearn that. In electrical engineering, it is always rho. What did you use for your azimuth angle, your angle in cylindrical coordinates? Theta. Unlearn that. It's phi. Right? In electromagnetism, a point in cylindrical coordinates, so first let me draw my Cartesian coordinates to show the correspondence. A point in cylindrical coordinates is rho, phi, and z. There are hundreds of different conventions for describing different coordinate systems. This is the one that electrical engineers have chosen to use, and electromagnetics engineers especially. Don't worry about it. Any engineer can work with any convention if you know the fundamentals right, so it's not that big of a deal. Everything else you learned about the cylindrical coordinates is still valid. So what do these correspond to? Well, if I drop this point down like I had an overhead light and put a shadow on the xy plane, rho would be, of course, that distance. In fact, it should solve, they put vectors here to denote that these are directions. This should solve the Pythagorean formula with respect to your x and your y coordinates. X squared plus y squared is equal to rho squared. That's one way to convert. Phi is measured from the x-axis and this one, if you wanted to calculate phi given a Cartesian point, what you would do is you take the arctangent of y over x if x is positive. If it wasn't, you would take the arctangent of y over x and you'd add pi to it if it was negative. And of course, this is probably an ambiguity that you've run into before. When your point sweeps around to the second or the third xy quadrant, there's an ambiguity in tangent. Remember, tangent only repeats itself every 180 degrees. So if you take the arctangent of something, you're always going to get something between minus 90 and plus 90, something that's going to place you here and here. So this little adjustment will allow you to calculate the full 360 degrees range of phi, your azimuth angle, as it is properly known. And this is just basic geometry. Of course, the elegant programmers among you have probably already figured out that, if you want to do this in MATLAB, arctangent will tell you the arctangent. But if you don't want to have to deal with this kind of contingency, MATLAB or any other programming language will usually do it for you. There's almost always a universal function called arctangent 2D or arctan2, where you put the y and the x in separately, and it'll calculate this for you. Convenient, isn't it? So yeah, that's our cylindrical coordinate system, and that's how you describe a point in cylindrical coordinates. Now, we don't want just a point in cylindrical coordinates. We would like to do some other things. We would like to be able to integrate in that coordinate system, because we're going to have to for this problem. And the other thing that we're going to have to do is express a vector solution in this coordinates, because the whole reason why we use these coordinates is that a lot of the problems that we study in electromagnetism are very complicated in, say, the Cartesian coordinate system, but they become almost, the solutions almost become trivial to express in the cylindrical coordinate system. And the reason why that is that unlike the Cartesian coordinate system, all these other coordinate systems have corresponding unit vectors that change their orientation depending on where your point of observation is. So if you think about it, Cartesian coordinate space, no matter where you go to, if I got an x here, a y here, and a z here, I can move in any direction, and those unit vectors always point in the same direction. Not so with the cylindrical coordinate system. First of all, I should sketch in my third coordinate z, the height above the xy plane. That's the same as the Cartesian z. But at this point, if you go to this point and you want to express a field solution, you actually have, let me lower this a little bit so I have room to draw it. You have a unit vector that points away from the z-axis, rho hat. So you can see, depending on where your point of observation is, that rho hat is going to slide around in space, always pointing away. That's actually an important thing to keep in mind, because when you change into other coordinate systems, for example, when one gentleman asked, why did I take the z hat out of the integral? I was like, that's because I could in Cartesian coordinates. They're always constant. I can't necessarily do that with rho hat. I got to make sure that it's going to stay constant as I integrate all my variables. It can actually be a function of the point of observation. That will bite us several times in this class and make our life a little bit more difficult. But on the balance of things, properly understood, it makes our life a bit easier. Phi hat points in the perpendicular to rho hat, parallel to the xy plane, and really it points in the direction of increasing phi. In fact, all of these unit vectors that we express field solutions with always point in the direction of increasing just that position dependence. So the rho hat points in increasing rho, the phi hat points in increasing phi, and the z hat points in increasing z. Up here like this. And they are all, of course, mutually orthogonal to one another. In fact, rho hat crossed into phi hat should be equal to z hat by the right-hand rule. Everybody know the right-hand rule yet? We haven't taken a cross product yet in the course, but I'm sure you've done it in physics. In this class, do not be afraid to use the right-hand rule. On that test, I want to see you whipping those fingers out. Don't be embarrassed. Everybody, we're all friends here. We're not going to think you're flipping us off or anything. Use that, because I can't figure this stuff out unless I see it. So I watch you when you take your tests. And some of you are almost ashamed to do it. You're like this. Don't be ashamed. Hold it high. I should give extra credit for anybody that holds it high and does it on the test. No, I won't. I'm just kidding. Yeah. Gonna have like a rave or something going on. Woo! Be careful for what you say in your electromagnetics lecture. Okay. Now, that's where the unit vectors point. The other last thing that we need to talk about is integration with respect to our cylindrical coordinates. Because to finish off our problem, we're going to need to do that. Integration. Okay, here's the deal. There is a wonderful diagram in your book that explains this exquisitely. Picture is worth 1,000 words. And when you get into these advanced coordinate systems, there's a picture for each of them that will help you out whenever you try to integrate something. And the picture looks like this. I got my x, I got my y, I got my z. And I go to a little volume in space where I want to integrate with respect to. So if I draw this little volume out, it's drawn as kind of like a bent prism in such a way so that the edges of the prism correspond to increasing r and z and phi, or rho and z and phi, I should say. So for example, if I want to slide this way, if I want to integrate along rho, I need to pick up a d rho. That edge of the prism is labeled that way. If I want to go up, this edge of the prism is labeled dz, increasing z. And if I want to integrate around like that, this is rho d phi, and that rho must always be there because this contribution gets bigger the farther I move away from the z-axis. Just a little bit of sweep in phi picks up a lot of distance when I move away from that z-axis. So that's why that term has to be there. And if you think about it, it has to be dimensionally correct anyway, right? I'm integrating with respect to distance in the coordinate systems. So all of my units should ultimately have units of meters, right? In SI units. Can't tell you how many times my undergrads do stuff like this, integrate with respect to d phi. They think it's position, but it's not. You'll get points taken off. Okay. So I like that diagram because what it allows you to do is, depending on what you're trying to integrate, you just pull chunks off this diagram. If I want to integrate, do a volume integration with respect to spherical coordinates, I know that my dv is going to be the multiplication of all three of these elements, rho, d phi, dz, and d rho. If I have a surface integral, well, it depends on where my surface is aligned. If I'm doing like a surface that's angled with respect to x and y, parallel to the z-axis, then I'm sliding along this facet, and I got to do dz times d rho. If I'm doing a disk, these cylindrical coordinates are very useful for doing disk-type integrations. And that means that, I'm going to have to spin around phi, and I'm also going to have to slide up and down rho. So in that case, I got to use this element of integration and this element of integration. It becomes rho, d phi. And sometimes my surface is a cylinder, the outer edge of the cylinder. And in that case, I'm picking up this facet out here. That before I was doing this with my circle. Now I got to pick out the outward facet. And in that case, my surface integral becomes rho Yeah. Rho d phi dz. Picking up this component and this component. I don't need to do anything with that. So if it helps, go ahead and draw this diagram for yourself and look at the problem at hand that we're gonna study. For our particular problem, we need to do a surface integral, and it's a plane. Let's see how we set up the problem. It's a plane whose edge is parallel to the z-axis, but is otherwise flat. And so we are actually going to pick up this contribution here. That's our surface element of integration. So now armed with the cylindrical coordinate system, let's finish off this problem. We go back to this, and we notice that we have done a coordinate change such that the z-axis is along here, y is pointing up. So I'm going to change our canonical result to reflect that. We've got to have y hat to denote the E field that points up away from this charge. And actually it points down because this is a negative charge density, and that's reflected in the sign change there. So we got an E field pointing down, uniform all above the chip. And then we'll have a crazy E field kind of pointing away from this but bending around above the chip surface. And it'll depend on this angle phi naught. So now let's calculate E1. We've got all the tools to do it. In fact, even before that, let me put the steps up here, because we're going to even go to a more complicated problem after this, one in the spherical coordinate system. But in the end, it's all just a recipe. Step 1 for this problem, identify integral type. Argument, and the kernel, or the Green's function, for those with a little more mathematical sophistication. In this case, we've got a surface charge. We need to do a surface integral, and we have that same Coulomb Green's chart function that we use in all of these, the rho minus a rho prime over rho minus rho prime magnitude to the third power. 2, define the region of integration. Where in the real volume is that r prime vector going to have to slide around and pick up all the contributions? In our case, we've got a square. It's an L by L square resting in the rho z plane for a fixed azimuth angle phi naught. 3, once you've done that, write your integral in terms of your point of observation and your point of integration, your variable of integration. Step 4, insert your scalar position vectors. Five is simplify. This is where you can apply a lot of your symmetry arguments and other assumptions to simplify down the problem. And then presumably, if we were going a little bit further, we would evaluate. But for this particular problem, you won't be able to evaluate this by hand. So this is where you put it in the computer. It's okay. Now we're ready. So E1 as a function of arbitrary x, y, and z is going to be equal to the surface integral, call it surface S1, rho sub 1, our positive charge density that is uniform, we'll assume, along the table. Truth be told, it actually is non-uniform, especially when it starts to dip down. Some of the charges kind of rush to one side. This is a good approximation for shallow angles. Times our kernel, r minus r prime, over 4 pi epsilon naught, we're going to be in free space, divided by magnitude of r minus r prime, quantity cubed. And that's integrating with respect to a surface element of integration. In fact, we said, let's put in the limits here. So we're jumping down to step 3 still. We're still writing our integral. It's going to be a double integral with respect to the z direction as I move away from the axis, and then the rho direction as I move away from the axis, and the z direction as I move this way. So I'm going to have a dz prime variable of integration and a d rho prime variable of integration. Since I've aligned the problem in a nice way, from z, the limits of integration are going to be from 0 to L. For rho, they're going to be something a little bit different. I got to go in here, and I'm going to change something up a little bit. On this problem, I'm going to pick this point in such a way that whatever my angle is, phi naught, whatever angle that table plate makes with respect to the z-axis, so pretend I could draw a line straight down there, this will always intersect the z-axis. And when I do that, depending on what phi naught is, I have to move this table point away from my z-axis to compute it. Does that make sense? It just helps to simplify things greatly so that I don't have to have variables of integration inside some of my limits of my integrals. That's always a much more pleasant thing to deal with. So what is this distance from here to here? We're going to have to use a little bit of trig, right? So if this is the angle, phi naught, and this is my distance d, then if this is going to intersect the z-axis, this distance to the center pivot right here is going to be d divided by the sine of phi naught. And what's more, I got to move plus L over 2 in that direction and minus L over 2 in that direction. So my actual limits are, when I go back to my integral, d divided by the sine of phi naught minus L over 2 d over the sine of phi naught plus L over 2. And while that may look complicated, it's actually quite simple because these are all constants. I'd much rather have to deal with constants than variables. Ah, yes?
You're evaluating the E in the cylindrical coordinates, right?
That's right. Well, we are evaluating the variable of integration in cylindrical coordinates.
But do we still need x, y, z then?
Yes.
Okay.
And here's one of the big themes of the course, okay? You do not need to convert your point of observation. You can keep your point of observation in Cartesian coordinates. Usually it's the variable of integration that you slide around to express the final solution, to do the actual computation. If it helps you, you can look at the solution at the end and say, oh, you know, this would be easier if I expressed it with rho hat and x hat and z hat. But we're going to stop before we can make that judgment. And in fact, in this generic problem, I can tell you it doesn't matter what coordinate system you express the final answer in. It's going to be too complicated for pen and paper. So you might as well just leave it in x hat and y hat and z hat, because that's much more convenient. And I'll show you what I mean when I work through this. Yeah, Cameron.
So when we do d divided by the sine of naught, that gives us the hypotenuse from the edge to
Yeah.
where that would intersect the plane.
Exactly. D over sine phi naught is that distance from there to there.
Uh-huh.
So we're going to integrate from that distance minus L over 2 to that distance plus L over 2 across this angled phi equals phi naught plane.
Okay, so that's why I was kind of confused as the point of reference where you were subtracting L over 2 and adding L over 2, because it seemed like you were taking that portion away and using everything else instead of taking everything else out and just using that L over 2 portion.
Yeah. So we kind of adjusted our limits of integration to take that into account so that we're in that proper square, 0 to L. And of course, this is also a difference of L apart. We're just conveniently moving the point away from the z-axis so that we can use this really nice simple integration formula rather than something a little more difficult. Okay, so now, point of observation, recall, is x, stick it on the x, y, stick it on the y, z, stick it on the z. R hat, or R prime, I mean, we got to get this, not the vector elements, but the positions, the variables of integration into the cylindrical coordinate system. Well, that's actually pretty easy. We just use our standard formulas to convert from Cartesian to cylindrical. Guess what? Z prime is still Z prime. That doesn't change. X prime is really rho prime times the cosine of phi prime. I'm going to prime everything here because remember we're talking about the variable of integration. Y prime is equal to rho prime times the sine of phi prime. You find these book formulas in your book or just use elementary geometry to reason through them. So now let me go ahead and stick these into this expression here. Rho prime is then equal to, R prime is then equal to rho prime cosine of phi prime. But you know what? I'm not going to put cosine of phi prime because according to the way, yes?
For R prime, is that supposed to be Y prime Z hat?
Oh, yeah. No. Of course not. There we go. Much better. Thank you. So for this one, I'm not going to put cosine of phi prime because in all this problem, I'm sliding around a constant phi equals phi naught plane. Phi is not changing. I'm not integrating with respect to it. It's a constant throughout this entire integration. So I'll just put my constant phi naught in there. Stick it on the x hat. Y prime is, again, rho prime, and I would normally put sine phi prime if I was integrating with respect to phi, but that angle is going to be held constant throughout all of this integration. I'm going to stick that on the y hat. And then finally, I have my z prime. Stick it on the z hat. So what do I wind up with? When I plug all this in, my final answer here is going to be rho sub 1 divided by 4 pi epsilon naught. In fact, I'm just going to take that outside the front because that's all a constant. What I'm left with in here is going to be x, my point of observation in the x, minus rho prime cosine phi naught. Stick it on the x. That's just subtracting these two vectors, r minus r prime. And I got to do that for the y component. And I got to do that for my z components. Notice I didn't pull any punches on this example. I didn't say, oh, we're only observing it on the z=0 axis, so this thing goes away. Or I didn't set things up nicely so that the symmetry drops out. I gave you the full-on generic charge of finding the entire E field in this space, at an arbitrary space. But it's nice because this final result you can actually use. So let me go ahead and finish this off. What's left? X minus rho prime cosine phi naught squared plus y minus rho prime sine phi naught squared plus z minus z prime squared, all raised to the 3/2 power. And we're done. This is where you put it in the computer and let that do all the hard work for you. It's this setup that counts. And now you can all go home and analyze DLP chips and the field that's around them. See you on Thursday. The way we left it off, we were talking about the cylindrical coordinate system. And today we're going to introduce the spherical coordinate system, all in the context of solving for electric field. Where we originally defined electric field. That's something that's proportional and points in the direction of any force that would exert on a charge present at that point in space. It's a very useful physical construct. And of course, it is caused by the presence of charge in a system, positive or negative. And so all the problems that we are solving now involve, here is an arbitrary charge distribution, point charges, line charges, surface charges, volume charges. What is the electric field that surrounds it at any arbitrary point in space? So that's the problem that we've been solving. And it gets very mathematical, right? But it's actually pretty straightforward. You just have to be systematic about how you approach it. So we're going to work another example today. And this time it'll be in the spherical coordinate system. This will be a coordinate system that lines up well with the geometry of the given problem. So, the first couple problems we worked on this involved Cartesian coordinates. It was things like lines on the z-axis, sheets on the xy plane, very Cartesian in the way they are set up. Then last class period we did an angled plane, which turned out to be easier to cast in the cylindrical coordinate system. And the one we're going to do today is a cone. So let's go ahead and write this problem on the board. A biconical surface charge is defined by the regions theta equals 45 degrees and 135 degrees, and r is less than, say, 0.5 meters. The upper cone has a positive surface charge density on it, plus rho sub s. The lower cone has a negative and equal in magnitude surface charge density, uniform across the whole cone. Remember, this is just a constant coulombs per meter squared. Fortunately, this is not one of those problems where I give you a rho sub s that's a function of space. It would be fair game. It could happen. But this is straightforward enough. Good for starting out on the problem. And so the question is, what is the E field on the xy plane? So let's sketch this scenario. I have x, I have y, and I've got a little bit of the spherical coordinate system, which we haven't introduced yet in the class. I know you're familiar with it. already from some of your math classes and physics classes. But I'll go ahead and just do a brief review because, once again, you'll see that electromagnetics engineers like to screw up the conventions of things. We like to be different. So what was the distance away from the origin in your math class called in the spherical coordinate system? Was it R or rho?
R.
R. Okay, that we got right. That's right. So if you're a distance away from the origin, that's R. And the angle that we make, if you drop this point down to the xy plane, that angle, just like the cylindrical coordinate system, was feet. And the angle that you make, this is of course the azimuth angle, and the angle that your point makes with the z-axis, if you draw a line from the observation point here, that's a unit r distance away from the origin, the angle between that and the z-axis is theta. This is your elevation angle. And in the electromagnetics convention, elevation angle is always measured from the z-axis. So that's 0 degrees. 90 degrees is you're on the xy plane. 180 degrees is you're going straight down on this diagram in the negative z direction. And pretty much you don't need to have any theta value greater than 180 degrees, because then you start bending back in on itself. And you actually don't need to do that, right? You can just make azimuth at 180 degrees to get over to that side of the world. So generally speaking, theta goes from 0 to 180 degrees, and by convention, the azimuth angle goes from 0 to 360. So that's the basic setup. So before we even get a little bit further into the spherical coordinate system, let me do a diagram that represents this scenario. I have the origin. I have x hat, y hat, z hat points up here. I drew it a lot longer, but that's because of the cones that I'm about to draw. I said this is a conical surface, a biconical to two cones with the tips touching. How do I know that? Well, I said that here's what defines the surface. Theta is equal to 45 degrees and 135 degrees. So 45 degrees away from the z-axis, I have a cone. And in fact, if I just hold theta equal to 45 degrees and let phi and r spin around and be whatever they want, that set of phi and r's will define a cone. Anywhere as a surface of revolution around that cone. The only difference is that I've clamped it down so that once you get to r equals to 0.5 meters, it stops. So this area here, which has plus rho sub s charge on it, little positive uniform charges all over the place, constitutes my upper cone. Now, 135 degrees, I have the exact same thing. That would be, of course, 45 degrees from the negative z direction. And I have a symmetrical cone that's all the way to 0.5 meters on the end. Let me draw this a little bit better. This is, and keep in mind, this is a surface, so it's kind of hollow. It's kind of like one of those really low-budget cones that you get out of the drinking fountain. You know what I'm talking about? You ever see one of those office coolers? They just have a little paper cone, and you put water in it. And it holds barely nothing because the volume of a cone is only 1/3 of a cylinder of its same height. It's very tricky. Very tricky. Negative rho sub s is the charge density down here. Negative charges. So, of course, the total amount of charge here is equal and opposite to the total amount of charge on the top symmetrical cone. And we notice a couple things about this problem. First of all, this would be a bear to work in the Cartesian coordinate system. Thank goodness for the spherical coordinate system. The other thing I'd like to point out, too, is that this is a nice canonical problem. Heck, this is a nice conical problem. But this is not just some sort of made-up thing. What might we use a problem like this for if we wanted to analyze what? Well, I actually brought in an example last class period, but I forgot to bring it down now, of a bicone antenna. Two pieces of metal that you resonate against one another at RF frequencies, and it sends out waves that travel all over the place, and actually makes a very good wideband antenna. So that you can actually use some of this analysis to analyze the near field in that system. Keep in mind that in our electrostatics portion of this class, we haven't allowed the charges to move yet. Everything is kind of fixed in space. As soon as you have time variations, you introduce magnetism and some other higher order effects, the coupling of fields and radiation, and it gets a lot more complicated. So how is it that we could take an electrostatic analysis and apply it to an antenna like that? Well, it turns out there are these radiated modes and circulating modes of power, and one of the core modes that exists very close in to an antenna is often called the quasi-static field, which kind of behaves as if the dipole antenna was like a capacitor. You put a bunch of charges on the top, and then you put a bunch of negative charges on the bottom, and there's a field solution around there that you can model. And it resembles, in its mathematical form, the amount of the quasi-static solution with a cosine 2 pi ft slapped onto it. So we could take this analysis, slap cosine 2 pi ft, and we'd maybe be able to understand the field distribution close to this antenna. That's actually very important for things like specific absorption ratio and some of the tests that they do on, say, antennas and cell phones to make sure that you don't absorb too much energy in human tissue. Every consumer electronic device that is a handheld unit goes through some sort of specific absorption ratio testing just to make sure that you're not cooking the customer. So you see where the hot spots is. And it's actually not the far field radiation that you're worried about mostly in that scenario. It's what are the fields doing near field, which look quite a bit different. They're not traveling waves, they're circulating waves. It's kind of what the field solution around here is going to be. We're going to find the E field on the XY plane. So basically anywhere on this infinite plane parallel to that disk that I just drew. We'll go to a point XY away from the origin, and then we'll measure the total field strength. Okay, so let's continue on with a few more facts about the spherical coordinate system now that we've motivated our problem. First of all, we'd like to be able to convert our points to and from the spherical coordinate system. So let's say, hypothetically, that I had a point in the spherical coordinates. I gave you a distance from the origin, r, a theta elevation angle, and an azimuth angle, phi. In that case, x is equal to r sine theta cosine phi. Y is equal to r sine theta sine phi. And z is equal to r cosine theta. If I wanted to go the other way, here's a useful set of formulas. R is equal to the square root of x squared plus y squared plus z squared. Theta is equal to the inverse cosine of z over r. Or you could say inverse tangent of z over the square root of x squared plus y squared, if you hadn't computed r yet. It's geometrically the same thing, just using the Pythagorean formula and a little bit of trig. And phi is the exact same formula that we used in the cylindrical coordinate system. It's that arc tangent of y over x if x is greater than or equal to 0, and the arc tangent y over x plus pi if x is less than 0, to absolve that 180-degree ambiguity in tangent and get the full 4 quadrants in the xy plane for that coordinate. Okay. Now, in our spherical coordinate system, we have 2 reasons why we need the spherical coordinate system. One is that to perform integrations on spatial variables like r, theta, and phi can be a lot more convenient for some problems than the Cartesian counterparts, x, y, and z. Clearly, whenever you see something that's spherical or conical or something like that, then it's clearly going to help out to adapt it to this type of geometry. Those problems are a bear to set up in the x, y, z coordinate system. You remember the kind of problems that we solved in Cartesian space. They are always planes or cubes or lines or that sort of thing. So that's helpful. The other thing that's good is that the actual final result that we get for our fields, our E fields, our rho, theta, and phis, are sometimes better expressed in unit vectors that correspond to the spherical coordinate system. So for example, the unit vector r hat always points in the direction away from the origin, basically in the direction of increasing r. There is a unit vector theta hat which points in increasing theta, which would be measured away from the z-axis. That's why it's going downward. And then, of course, if I draw with a little foreshortening here, I got a phi hat that points kind of into the board, and that's direction of increasing phi. So if you can imagine, my r, my phi, and my theta here make a right-handed coordinate system, and all of those vectors change their orientation depending on where I'm observing them in the spherical coordinate system. So that's tricky. That's tricky. That's a nuance of vector calculus that you've probably run into before. In fact, we saw a glimmer of it when somebody pointed out, like, I had a z hat unit vector, and it was inside of an integral, and I was able to take it out here because I treated it like a constant. You can always do that in Cartesian coordinate system, but you can't necessarily do that in other coordinate systems, because sometimes these are functions of your points that you're integrating with respect to. You just have to test it out. But there are some problems that at the end, when you're finished expressing them, it might be actually easier to express in this type of coordinate system. Now, I'm going to draw another diagram similar to last class period. Do you remember I did this one when you perform integrals in spherical coordinates? So if this is the origin, and you go out to some arbitrary point in space, and you need to pick up elements of integration. This is even a little bit more complicated than the cylindrical coordinate system. And I like to make these diagrams because they really help with the understanding. So if you're picking up this dimension, that's the dimension of increasing r. That's dr. If you're in this dimension here, picking up basically a dimension of increasing or decreasing theta, this is going to be, right there, r d theta. Why do we need an r? Well, clearly we need one because we need units of meters if we're integrating in a spatial domain. And secondly, this is kind of like the radius formula, the arc formula for distance as a function of arc length and sector width, arc radius and sector width. Because a slight change in theta makes a much bigger difference when the r is big than when it's small. So I need that scaling factor in there. It's kind of like the rho d phi we had in cylindrical coordinates. Now, speaking of azimuth, if I'm picking up this dimension here, the perpendicular dimension of increasing azimuth, the element that I need there is r sine theta d phi. Well, clearly I need an r because, again, if I move farther away from the origin, a small change in my azimuth angle is going to make a big difference in the space that I traverse. So that scaling needs to be there. I also need to scale it with respect to my theta. Because when theta is equal to 0 degrees, or a very small degree number, it's pointing almost straight up in the z-axis. And so when it spins around, it doesn't cover that much ground for a given radius. If you take that same radius and bring it closer to the xy plane, where sine of theta is close to 1, you swing it around, you sweep out a lot of distance. So I got to scale it with respect to r, distance from the origin, and also the azimuth, the elevation angle, as measured from the z-axis. And so that's why that sine theta d phi term comes in here. So if you want to, do you have a question?
Yeah, the r sine theta d phi is measured across the horizontal plane, right?
The r is the distance from the origin to the observation point. Theta is the angle that makes with the z-axis.
Right.
And d phi is your element of integration there.
I was trying to figure out where the arrows...
Oh, this, yeah. So this is a remarkably, with near computer-like accuracy, a 3D rendering of this element of integration. So if you can, it kind of goes into the board.
Yeah, so like if it were here, it would be like this.
Yes, yeah, that's right. So this r d theta is kind of like this. The r sine theta d phi is kind of like this. And then the dr is increasing in that direction. Somebody needs to invent the holographic blackboard. That's your next charge as engineers, the holographic blackboard. I'll be your first customer. Okay. Another thing that I'd like to remark upon is about expressing field solutions in different coordinate system vector spaces. So for example, if I wanted to express an electric field in the spherical coordinate system, then I would have a radial component to the field as a function of whatever point of observation in 3D that I was using. That, of course, would be on the r hat direction. I would have a phi component, and that would be in the phi hat direction. And I would have a z component, and that would be in, theta component, and that would be in the theta hat direction. There are some problems that it's actually much easier to decompose a field at a point with this kind of sliding spherical coordinate system. You could probably think of a couple examples right off the bat. Coulomb's law for point charges, much easier to express that solution in the spherical coordinate system by just saying that, the E field is charge over 4 pi epsilon naught distance squared times r hat, because it always points away from the origin if the charge is centered there. If you express that exact same solution in terms of x hat, y hat, z hat, field decomposition vectors, it's an algebraic nightmare. So the other thing that I need to remark on, and this is a common error on tests and early homeworks in this class, so be aware of this, is that always try to distinguish between the point of observation in space, which in these things are your R vectors, and the actual field decomposition at that point in space, which is a completely different vector. We have vectors that are functions of vectors. The inputs are the space vectors that tell you where the position that you're making your observation is. And then the outputs are these vectors that represent field and hence forces on charges that would be placed there. So these have units of volts per meter. These unit vectors are unitless, right? This doesn't have units of meters because it's got an R on it. It's R hat. It's unitless. It just points in the direction of increasing R. This doesn't have units of radians. This does not have units of radians. These are just directions, unitless directions that point in the direction of increasing phi and theta. And they're useful for decomposing fields. Now, as we saw last class period, it is perfectly okay to integrate your problem, do your Coulombic integral in, say, the cylindrical coordinate system, but leave your field expressions in terms of x hats, y hats, and z hats. Nothing wrong with that. So students get really bent out of shape when they see that. They're like, oh my goodness, you've got to be doing something illegal. Like, nope. You can mix and match your vectors and your field expressions. I think we'll probably do that on this example too. So just also to help you facilitate your field analysis, if you are given this vector and you want to convert it into the Cartesian coordinate vector expression with x hats and y hats and z hats, or if you want to do vice versa, very easy to do. There are these little tables in your book, these little dot product tables. Rather than give you a whole mess of formulas to memorize, it's actually easier to use these little dot product tables. And these basically tell you what are the dot products, depending on your point of observation, for the different unit vectors that you're looking at. So we've got r hat, theta hat, and phi hat on the column headings. And then on the row headings, I have my x hat, my y hat, and my z hat. And I'll go ahead and fill in what your book says is the dot product of these. Remember, the dot product is basically the projection of one unit vector onto another unit vector, and it's going to give you a scalar. And somebody has gone through ahead of time and done all of the math for you so that you can say that sine theta cosine of phi is the dot product of r hat and x hat. Theta hat and x hat is cosine theta cosine phi. And that dot product with the x hat is minus sine phi. And let me just keep on filling in these. We don't have to beat a dead horse. And the dot product of z with theta hat is 0. Why? Because they're all always orthogonal to one another, right? Z always points up. Theta hat is always pointing somewhere parallel to the xy plane. That's why that's always 0. Okay, so how did you use a table like this to actually compute a field decomposition? So here's how you would do it. Let's pretend you wanted to convert a spherical coordinate system, that field vector that I had up there, into an expression in the xyz coordinate system. And let's just do it for x. So Ex as a function of three-dimensional space, x, y, and z, wrapped up in that nice shorthand notation, r with a vector on it, is equal to x dotted into my full vector field expression. That's really, when you take a unit vector and dot it into a vector quantity, you're pulling out the projection in that direction, the magnitude of that vector in that particular direction. Yes?
Sorry, you said that table over there is for cross product or dot product?
Dot product. So, of course, the x component would be x hat dotted into that full vector. Now, if this was my spherical coordinate expression of a vector, and I wanted to convert it to Cartesian, what I could write this out as is my r component as a function of three-dimensional space. And, of course, that's on the r hat unit vector, and I dot that with my x. And then I have my phi component as a function of three-dimensional space, and I'm going to dot that with my x hat. And I have my theta component, and I'm going to dot that with my x. So all I'm doing here is just distributing this x hat, because I'm pulling the x component out of it. And this is where I go and I look at my dot product tables and just replace all of these with the expressions in that table. So in the end, what I've got, if I read that table across, ER, and I'm going to drop the positional dependence because I'm going to run out of board space otherwise, sine theta cosine phi minus E phi sine phi plus E theta cosine phi. And I'm just pulling those off the table there, making a straight up substitution. This is my EX, the part on my x hat field expression. Then if I wanted to complete the conversion, I do the exact same thing for y hat and the exact same thing for z hat. Kind of algebraically intensive, but very straightforward. And it's nice to do it that way instead of like having 9 different formulas on the board. Yes?
Should that be sine phi?
Let's see. I can't see the board. Should it be sine phi? Oh, yeah. I read the wrong thing. One of the problems is you cannot see the board over there when you're really close to the board. So I make a number of transcription errors that way. Okay. So now that we got all that out of the way, I think we're ready to finally solve this conical problem. You ready? Okay. Here's our conical problem. What I'm going to do, first I'm going to apply some symmetry arguments here. We're asked to find an E field on the xy plane. And it's nice because my point of observation is now going to be x on the x hat, y on the y hat. I'm going to leave this in Cartesian coordinates for the time being, and 0 on the z hat. And then, of course, I'm going to have to slide my variable of integration, my r prime, and I'm really going to have to slide it up and down 2 different integrals. I got a top cone with positive charge and a bottom cone with negative charge. So I'm actually going to use some superposition here. I've got integral number 1, which will be my top cone, and integral number 2, which will be very similar looking, but it'll be my bottom cone. So let's go ahead and set that up. E field as a function of r is equal to a surface integral of rho sub s as a function of r prime, my variable of integration. I'm integrating on cones, and my kernel for this integration is r minus r prime ds prime 4 pi epsilon over the magnitude of r minus r prime squared. Cubed, excuse me. And bless you. Now I'm going to break this apart into a top cone and a bottom cone. I'm going to recognize that this is my rho sub s, so I'm going to pull it out. I've got a constant 4 pi epsilon that's going to pull out as well. Integral, and I'll just put top cone here to denote that's the surface. And let's see, I'm going to have x, stick it on the x hat, y, stick it on the y hat, no z component, and my variable of integration is going to be x prime, stick it on the x hat, minus y prime, stick it on the y hat, minus z prime, stick it on the z hat. So at least I was able to make a little bit of simplification by saying my point of observation is always z equals to 0. Okay, that's the top cone. Now I need a bottom cone, and that's going to look very similar, but remember this changes sign, so I'm going to have a minus rho sub s over 4 pi epsilon, bottom cone, and otherwise a very similar looking formula. Okay. Whoa, that looks hideously complicated, doesn't it? Let's go ahead and make it a little bit simpler. According to this, my E-field expression, I'm going to have this integral of this vector, and it's going to have all these spatial dependencies underneath. However, I got a couple simplifications that I can make. First of all, let's look at that cone problem. I got exactly the amount of positive charge on the top half and at the bottom half. And I'm observing midway on the xy plane between them. Which direction is the final E field going to point? Down. Down? That's right, that's right. So if you think about it, let's go over to this picture. Let's say I go to a point on the xy plane. I have a positive cone. It's going to make an E field that points this way. Just say, hypothetically. That's right. Yeah, it's away from the cone. So imagine this is, in the plane of the board. It'll be away from the cone. If you have a negative charge, you get the exact same. If this was a positive charge, that would make a component that points the exact same magnitude, but upward. However, it has negative charge on it. So that is going to be in this direction. And the resultant should only have what we hope to be a negative z component. So even though this looks really complicated over here, I know that all of this stuff, without even integrating it, it's going to go to 0. Lamb, do you have a question?
Oh, it's just my hand by saying doorknob, but actually, since you called it doorknob.
Yeah, I got it.
But since you called me, like,
That's an interesting way to relax in class. I like it. I like it.
So, you're saying, I'm not quite completely following the picture. Like, this is a cone that's like this, right?
That's right.
Like this. And then you're saying that one is pointing out this way.
Yeah, so you got a bunch of charge. Let's forget about the shape. It doesn't matter what the shape is. It's actually the symmetry of the problem. This one up here is a cone. It's going to point, kind of away from the cone. We don't know exactly the direction. I just kind of guessed in that way. And this cone down here, equal and opposite in charge. If it was the same charge, it would point that way. But instead, it's going to point equal and opposite in the other direction. So the resultant will be in Z. Negative Z to be exact.
Okay, because you're using the thumb thing.
Yeah.
Okay.
Fields always point away from positive charges and towards negative charges. So this was a remarkable simplification that we've been able to make. We can even make a few more. First of all, we recognize from our spherical formulas that we put on earlier in the class, we are going to substitute Z prime is equal to R prime. Let's see, what was that formula? Cosine theta prime. And let's see, what else do we need? We need an X prime. And a Y prime. So we can integrate these variables of integration with respect to the spherical coordinate system, because that's what conveniently lines up with what we're doing. Who had it first? You. Oh, you.
I'm kind of confused at how that whole section goes to 0, because when you're taking it into respect of the top cone and the bottom cone, shouldn't the top cone itself have some XY component and the bottom cone itself?
Yes. That's a really good point. These go to 0 because they cancel each other out, not because they do individually evaluate to 0. That's an excellent clarification. Collectively, they go to 0. I should draw something that kind of denotes that.
The top, the X and Y collectively go to 0, and then the Z kind of stacks on each other because it's negative.
Yeah, in fact, you see, you kind of have a double. What we're going to find, let's go ahead and just do this right now. Get it over with. In this integration, our theta prime is always constant. For the top cone, it's 45 degrees, or pi over 4. For the bottom cone, it's 135 degrees, or 3 pi over 4, right? So if that's the case, then I can always write this. What's the cosine of pi over 4? Yeah, 1 over the square root of 2, right? Perfect. And let's see, let's do that here too. What's the sine of 45 degrees? Yeah, same thing. How convenient. This is all the square root of 2. And this is for 45 degrees. That's the top cone. For the bottom cone, I got 135 degrees. And in that case, Z prime is equal to R prime times the cosine of 135 degrees. Well, that's negative 1 over the square root of 2, right? So I got to have negative R prime divided by the square root of 2. And then X prime is going to be equal to the sine of 135 degrees. Well, that's positive 1 over the square root of 2. You guys all remember in your trig formulas? Yeah, not too bad, right? Not too bad. Okay, so I was able to at least turn that into a constant. And then I can see why the Z doesn't go to 0. Because I got a negative sign here. And when I plug this into here, on the bottom, I got another negative sign. So 2 wrongs make a right in mathematics. And they constructively add to that component there, which doesn't change signs either in charge or in the Z prime. So let's go ahead and write this out again with our simplifications in mind, okay? And it'll start looking a lot nicer. Oh, one more thing we got to do. What is our ds prime? Conveniently, and I was about to erase it to do the rest of our problem, we have our little diagram up here. How to integrate stuff in the spherical coordinates over here. I got a dr, and I need that dr because I'm going to be sliding up and down my cone as I pick up all the contributions of charge. And let's see, I need this, r sine theta d phi, because I'm going to be sliding around 0 to 2 pi in phi, picking up all that conical charge. I am not going to need this, though, this r d theta term. That's the element of the volume integration that I'm ignoring. I'm holding constant, because our theta is on a constant conical surface. Theta does not change, so I don't need to vary it in my analysis. So with this in mind, ds prime is equal to dr r sine theta, and these should all have primes on them, d phi prime. And what's more, we already said that for all the integrations, theta is constant. So that's my ds prime. Everybody understand that? How we got that? Now that I erased it? Okay. Now, electric field as a function of x, y, and z equals to 0 is going to be equal to just my z component, which I will now write as rho sub s over 4 pi epsilon integral from 0 to 1/2. The reason is we're going from 0, the point of the cone, to 1/2 meter according to the problem statement. So that should be my 0.5 meters there. It's going to be dr prime. I'm integrating my phi prime from 0 to 2 pi. I got to spin all the way around the world to get my cone. And what I'm left with, let's see, I got to have an r prime here. I got to have a square root of 2 in the denominator. I'm going to take my two z components, which actually double up. So let's go ahead and put 2 there, because I'm going to combine the results of those integrals. And then what's left? Let's see, I've got r prime over the square root of 2. This is my z prime. That's on the z hat direction, and there's a minus sign in front of it according to that integral. That's the only component, the vector component, that does not evaluate to 0 in the total integration. And then in the denominator, I got all this other stuff. I've got x minus r prime over the square root of 2 cosine phi prime squared plus y minus r prime over the square root of 2 sine phi prime quantity squared. And then I got to continue on to the next line. We're still not out of the brackets yet. Plus r squared over 2, which is my z prime squared. All that raised to the 3/2 power. Whew, let's go ahead and simplify this stuff. Let's see, I got a 2 here. I got a square root of 2 in the denominator and a square root of 2 down there. So 2 divided by the square root of 2 divided by the square root of 2 again is 1. Z hat is a constant. That's the nice thing about Cartesian coordinate unit vectors, and one of the reasons why we kept it in the problem so far is that we can take that out of both of those integrals. So let's write this. Rho sub s in the minus z hat direction, we'll go ahead and take the minus out. 4 pi epsilon integral from 0 to 0.5 with respect to r prime, integral from 0 to 2 pi with respect to d phi prime. And then what do we have left we just have r prime squared in the numerator and this mess of stuff in the denominator. I'll go ahead and repeat it for completeness. No, what we're doing this was the limits of integration for the top cone from 0 to 0.5. The limits of integration for the bottom cone are also 0 to 0.5, r equals 0.5, just with theta equals to negative, or excuse me, 135 degrees. So that takes into account the fact that it's below the plane. That's where you take into account the sign convention.
I missed. Where did you get the 2 on the top from?
Let's see, this one?
Yeah, that one.
So this 2 came from the fact that we actually had the same contribution from the top integral and the bottom integral. And so I cheated. I just said, I'm just going to write one integral, and I'm just going to double the result.
Oh, yeah.
Yeah,
so
that's okay.
The sum for the whole thing.
Yeah, that's right. And now I've basically said this is going to be the total contribution. So whatever this evaluates to is the sum of the z component on my top and my bottom.
Oh.
The parts that align up and reinforce because of symmetry. Yes?
For the z prime, the first integral, you have negative r prime. Why is it negative r prime?
Let's see, because we had a negative over here. That's where that negative came from. The other stuff I ignored because I knew it was all going to go out to 0 in the wash anyway.
You said the first integral is just for the 45?
That's correct. That's correct. But it turns out that for the 135, these are all the same in the denominator. These were sines, I believe, whereas that was a cosine, so that sign flipped and reinforced. Yes, Lamb.
I tend to vanguard things, like concepts, something people might be thinking. Just make this a little epic for just an example.
No, not at all. Not at all. Because we're done. We're done. This is our final answer. We do not have to evaluate it.
We can turn that in.
Yes, absolutely. This is now as simple as it could possibly get. Because here's the philosophy of this class. No, I'm glad you articulated that, Lamb, because this is the philosophy of the class. Any realistic example that an engineer is going to come in contact with is going to be hard because life is hard. So you just need to be able to set it up and let the computer, because this is what computers are for. Computers can't get to this step, but they can go from here to that step. That's what they're good at. This is what we're good at. Well, this is what we hope to be good at. Now, depending on where you got in this problem, you probably would have gotten like half credit if you had just kind of set this up and recognized that you needed to break this into 2 different integrals. You probably would have gotten 3/4 credit if maybe you had made it to here and put some values in, but maybe failed to see the symmetry that canceled. If you got to the final answer here, you get full credit. And if you got to like a reduced value that didn't have any integrals in it and was expressed in terms of elliptic integrals of the second kind or something like that, which I think what you need to solve something like this, you would have been my favorite student. You wouldn't have gotten any extra points, but you would have been my favorite student. Remember, it's just algebra. Technically, in none of these problems, we're not doing any integration. Right? We didn't even have to integrate. I hesitate to call this a vector calculus problem because we didn't have to integrate. We're doing algebra and setting things up. Okay. So who's scared out of their minds for the next test? This was actually a test problem of one of my previous classes. And you know what? They actually did pretty good on it, because after a while, especially after you do this next homework set, you're going to get really good at setting these integrals up. And we're going to do it again for voltage. We're going to do it again for the Biot-Savart relationship.
You posting that this afternoon?
Yes. Okay. Yeah. What you got?
Why is the top boundary 2 pi over here?
Why is the top boundary 2 pi? Oh, yeah. Because, okay, we're sliding. These are the r prime limits. So we're going from the center out. And then the 0 to 2 pi, we got to spin all the way around to pick up the cone. Keep in mind that it's phi, or phi prime, that can go from 0 to 2 pi, around the world, so to speak. It's the theta that can only go from 0 to pi. Because if you go past that, then you could have expressed that as just phi plus 180 degrees. Right? And the human coordinate system. You have to have no shame to use it, but it's much more illustrative than drawing stuff on the boards. Okay.